So, welcome back to Introduction to Photonics. In the last lecture, we started discussing about lasers. So, we said okay, lasers nothing but an amplifier with feedback, and we considered this simple case of gain medium. On either side of the gain medium, we had mirrors providing the feedback, and we said okay, once you pump the gain medium with an external energy source, then you excite these atoms in the gain medium, which can provide spontaneous emission, and those spontaneously emitted photons, when they get bounced by the mirror, reflected by the mirror, they come around and stimulate the transitions inside the gain medium, and then you have a buildup of stimulated emission photons. And then we said okay, it is not like all these stimulated photons survive within the cavity. We basically said that first of all, you get laser action when you are able to overcome the loss in the cavity with the cavity gain. So, that was one condition, and then the other condition was that we said if for this waves to be consistent inside the cavity, you have to essentially satisfy the constructive interference condition, and that essentially meant that only certain frequencies can survive inside the cavity. So, even though you may have other frequencies that are possible because of the cavity, that may be supported by the cavity, only certain frequencies whose gain is equal to or greater than the loss inside the cavity will survive within the cavity. Right. So, we talked about that concept, and then we said okay, it is probably better that we look at the saturation of the signal photons, or the saturation of the gain inside the cavity. So, we said okay, we may start at a relatively high inversion, right, which corresponds to a relatively high small signal gain. So, that small signal gain here is given by gamma naught. We may start from that point, but the moment you start having stimulated emission of photons, you start building up those photons, you start saturating the gain, right. This is a concept that we already discussed when we were looking at optical amplifiers. So, that gain saturation reduces the gain available to these photons inside the cavity, and correspondingly what we see is initially the output is it shoots up the moment the pump energy is turned on, and then your gain saturates. So, the number of photons inside the cavity reduces, and then when the photons reduce, the gain recovers, right. The gain is not saturated as much, so the gain recovers, and so it goes through these oscillations, what we call as relaxation oscillations, and then it achieves steady state. And at the steady state, what we are saying is whatever excess pump photons, you need a certain pump photons to provide the inversion necessary or the gain necessary to overcome the loss, but any excess pump photons are now contributing to the signal photons, and that is the output that we are seeing in the steady state. Okay. So, what we are essentially saying is, although you may be pumping at a relatively high level, okay, as far as the gain is concerned, the gain of the medium is concerned, the gain gets clamped at the level of the loss inside the cavity. Okay. So, like I said, any excess pump photons are contributing to the signal photons that are escaping the cavity. Is that clear? So, the question is, what are the typical time scales at which these relaxation oscillations happen? So, these relaxation oscillations happens a few cycles, few pumping cycles. Okay. So, what is the pumping cycle? You take a photon from a ground state to an excited state, and you stay in the excited state until the stimulated emission happens, and you come back to the ground state, and then you are pumping again, right. So, it's in the order of and that's determined by typically on one end with very few photons, it corresponds to the spontaneous lifetime, spontaneous emission lifetime. And on the other hand, if you have a lot of photons already in the cavity, then your stimulated emission, then it's a fraction of a spontaneous lifetime. So, these relaxation oscillation time period correspond to a fraction of the spontaneous lifetime. So, it will be in the order of a few tenths of microseconds typically, if you are talking about a system like a erbium system that we are now familiar with, from our discussion on the optical amplifiers. So, it's a few tenths of microseconds is what it takes to achieve steady state, and that for all practical purposes is not is a problem, right. So, we can hardly perceive that sort of oscillations, but there may be some applications where this may be something may be important to track. Okay. Then we went on to look at this picture a little more detail with respect to the pump power. If you are looking at the output power or the output flux, right. The output power, by the way, is denoted dependent on the output flux by what? You have the energy of the photon, that is the signal photon that you are getting out, multiplied by the rate at which the photons are escaping. And the rate at which the photons are escaping is not the same as the signal photons within the cavity, right. The photons that you get out is only a fraction of the photons that you have built up in the cavity. For example, if it is a high finesse cavity with a very high reflectivity mirrors, then you build up a lot of photons in the cavity, and you are actually leaking out only a few photons from the cavity. Okay. So, that is phi. When we talk about phi out, that is the signal photon flux that is coming out of the laser. It is actually a fraction of the signal photon flux that is present within the cavity. That signal photon flux is what we are tracking as phi s here, right. So, I can write, maybe I'll just go to the next page, I'll just come back to that. I can write here itself. Phi out is a fraction of phi s, and that fraction is determined by the loss of the mirror, right. So, if you are taking output at R2, so what is R2? If I just go back and look at this picture, this R2, this mirror, which we would normally call as the output coupler, right. So, that laser output, okay, is, if you are looking at that output, that is it's proportional to phi s, right, where phi s corresponds to the signal flux that is inside the inside that cavity, and that proportionality constant is dependent on let us say the mirror loss with respect to the overall resonator loss. You understand that? So, we are tracking only the fraction of photons that are coming through mirror 2, which is having a reflectivity R2, right. So, a fraction of that loss compared to the overall loss in the cavity is what we see coming out of that laser. Okay. Normally, what we try to do is, if you go back and look at this picture, you make this as a high reflector, right, make one of the mirrors a high reflector. So, you have very little light going out this way, you direct all the light to come out towards the right side. Okay. So, that's what we do. Now, we stopped at the point where we were looking at, from the threshold condition for a saturated amplifier, right. We basically were trying to get an expression for phi s, and phi s we said is given by phi sat, this is the saturation flux, multiplied by n naught over n t h. So, how much is the small signal gain over the threshold gain, right, because any small signal gain that you have beyond the threshold gain is actually contributing to the extra signal photons that you are having in the cavity, right, minus 1, right? And that is something that is happening for n naught greater than n t h. Now, I can represent that using another graph just to help you visualize this. So, when you are tracking n as a function of n naught, right, where n naught is the inversion that is available to you without any signal photons, right, that is the small signal inversion that you have, right, and that just is proportional to the rate at which you are pumping or the pump power, right. So, on the x axis you are increasing the pump power, and correspondingly in the y axis what you get to see is there will be a corresponding increase in the inversion that you have inside the in the gain medium, but that inversion gets clamped at a value NTH. Okay. So, that inversion will get clamped at that NTH value, because any further pumping is the inversion, which is basically N2 and the relative levels of N2 and N1 are clamped, and any further pump photons are essentially continuously giving signal photons out, right. So, that is essentially what is happening as far as this cavity is concerned. So, just to illustrate that, we have a question there. So, it is a good question. So, the question is, do you have only the signal photons coming out, or can you actually have pump photons also come out, right. So, any unutilized pump photons can also come out of the laser, and if you have designed your laser cavity well, you would have absorbed all your pump photons, but if the design is not so good, then you have the possibility of those pump photons also coming out, and then you would have to have a filter at the output, external filter, to cut off the pump photons. Normally, when you design these mirrors in this picture, when you design these mirrors, you design them to be highly reflective. Well, when we talk about high reflection and output coupling, those reflectivities we are considering for the signal photons. So, this is actually the reflectivity that we are defining at the signal wavelength, but you could possibly, if you want to conserve all your pump photons, you could probably put you can make them highly reflecting, both the mirrors highly reflecting at the pump wavelength. So, the pump photons do not escape the cavity, they are all just reflected within the cavity itself, right. We know that we have gone through this design of a dielectric thin film filter, right. You can make this stack of high and low refractive index regions, and you can actually put coatings such that it behaves or it provides a certain reflectivity at certain wavelength and certain other reflectivity at certain other wavelength. You can basically stack these dielectric thin film layers such that the one stack can give you, let us say, 50% reflectivity at 1 micron wavelength. Okay, let us say 1 micron is your signal wavelength, and let us say 0.8 micron is your pump wavelength. You can put another stack on top of that, which will reflect all the pump photons. Okay, so you can make your mirrors to be so these mirrors are typically dielectric thin film filters, and you can make the mirrors such that they provide different reflectivities at different wavelengths. Okay, so just to get all of these together, let us just go through a very simple animation, okay, which is showing how the this laser works, right. And once again we are looking at a Fabry-Perot cavity with a gain medium in between the mirrors. So, one is actually the atomic picture, and that red color thing around that atom is actually showing the excitation level of the atom, and towards the left side of your screen you actually see the energy level diagram. Okay. So, you are tracking simultaneously what is happening in the energy level diagram as we are exciting this atom. So, now it is actually going to that excited state. So, you can assume that some pump energy has been provided to this atom and it's taken to that excited state. And this is actually denoting a spontaneously emitted photon, right. This spontaneous emission may actually come from another excited atom within that gain medium. So, when that stimulation happens, you see correspondingly the atom is actually de-excited back to the ground state. Okay. Now, we are starting to build up stimulated emitted photons. So, now we go to a picture where you have multiple atoms. This is a realistic picture where you have multiple atoms, each of them could be excited. And what we have now is we have put mirrors on either side. So, these photons are reflected within the cavity, and you want to pay attention to the green squigglies, because initially it is spontaneously emitted photon. So, the periodicity is not very well defined, but what happens when you go through a few bounces. So what happens to the things is it's actually gaining coherence, because initially you may have spontaneous emission corresponding to several different frequencies, but as you go through these reflections, only those photons which are at specific frequencies that correspond to the round trip, that interference condition that we talked about, only those photons will survive. So this actually becomes more periodic. So if you can see that now you have not only so many photons, but they are all quite synchronous with respect to each other. And that is the oscillation that you have. And then you have output coupler, which is partially reflecting, so it is actually leaking out this thing. So this is actually showing as if the buildup is happening and then you suddenly turn the tap and you get the beam out. That is not what is happening really, right. So you do have, that was just for illustration purpose, but you have continuous streaming of output, but just to show the different processes, it has been put in a chronological order, right. So let us just quickly see that again. And towards the later part of that, you actually saw the wave that you had is actually a standing wave, right. So that is what happens in a real cavity. It is actually a standing wave. In the photon picture, initially you can think of these photons bouncing around, but in the wave picture, that actually corresponds to a constructive interference criteria, and it actually sets up a standing wave pattern inside the cavity. Okay, so that you can, whatever oscillation that you are seeing of the light that is coming out, that oscillation you can imagine is actually happening within the cavity itself. Okay, any questions about this before we move on? Yeah. So the question is, what happens to those other frequencies which are not coherent within that? They actually just die away. They are not getting any gain, but they are experiencing loss, so they just die away, right. So when you go through multiple round trips, they are discriminated against. They keep losing their energy, right. Only these particular frequencies are building up in energy, right? Building up in terms of numbers and the total power as well. Any other questions before we move on? Okay, so let's just get back to this. So the question is, we showed that the atom is de-excited to the ground state upon the stimulated emission. How much time does it take for the atom to go up to the excited state again? It just depends on the pumping rate. So the number of pump photons you have, the pump photons you have, and the probability of the transition, which is determined by the transition cross section, that determines how many of these atoms go back to the excited state again. You have to remember that the numbers that we are talking about are large. The numbers that we discussed, the number density of ions, 10 power 24, and the number of photons is in the order of 10 power 19, 10 power 20. So, you are looking at that many photons, this many ions. So, there is depending upon the relative quantities and the probability of the transition, that transition happens. Any other questions? Okay. So, let us just get back to this discussion. So, let us continue from where we left off yesterday. So, the question is, what is the slope, right? So, what is that slope, and that is typically what you call a slope efficiency of the laser. So, slope efficiency clearly determines what is the efficiency with which you are converting pump photons to signal photons. You want as large a slope efficiency as possible. Okay. That slope efficiency, I should mention, is related to one more common terminology that is used, which is called the wall plug efficiency. As a user of a laser, you do not want to worry about how much I am pumping, how many signal photons I am getting and all of that. You are, when you look at an eagle's eye view of this entire thing, you are wondering how much electrical energy that I am spending, how much optical energy am I getting, right. So, in this case, you can think of it as in terms of power. So, how much electrical power I am consuming and how much optical power I am getting. So, that optical power over the electrical power is called the wall plug efficiency. So, you want lasers to have a very high wall plug efficiency. To give you an idea, the wall plug efficiency of semiconductor lasers can be as much as 50%, okay. Whereas, you need to think about a gas laser, some of the earlier gas lasers like argon ion laser, the wall plug efficiencies is a fraction of a percent, because there you are trying to set up a discharge, and so you are spending a lot of electrical energy in setting up the discharge. And that discharge is effective in creating an inversion. Only a fraction of that power is getting converted to stimulated emission, and finally the optical power that is coming out. So, nowadays it's become very important, because we initially, whichever way you can get a laser, you got it, right. You just went about, I want a laser at this particular wavelength, and you did not bother about these wall plug efficiencies and all that. Nowadays, you cannot do that. Everything is driven by how much energy you use in the process. So, the wall plug efficiency becomes very, very important number, and what supports the wall plug efficiency is the slope efficiency. How well do you convert the pump photons into signal photons? So, this is right. Says I have run out of time even before I started my lecture. Well, that is the way it is. Okay, let us just stop right there, and we'll continue after 10 days. Okay, so hopefully you remember all of this until that time. I do want to mention one thing though, which is important for the lab session that you are going to have. What you will do in the lab session is not a Fabry-Perot cavity. So, here I have made a laser out of a Fabry-Perot cavity. But as far as the laser is concerned, you just take an amplifier, you provide feedback. You just loop the output back into the input. Okay. And that type of a cavity where you have taken the output of an amplifier and looped it back to the input is called a ring type cavity, or in short it is called a ring laser. Okay. So, what you will be building is a ring laser. You will just take the output of the amplifier that you already built, you are not giving any input, right. Take the output and you just connect it back to the input. So, when you pump that medium, there is going to be spontaneously emitted photons, and that is going to loop back and they are going to seed your amplification, okay, and they are going to stimulate the transitions in the erbium dope fiber, and then that is going to recirculate in a loop. Okay. So, what you will be building in the laboratory is actually a ring laser, and that is just an extension of the amplifier that you already learned how to build, right. So, it is a very simple extra step, but then now what we are looking at is what are the characteristics of the laser that you have built, like this, what is the output power as a function of input power, what are the spectral characteristics and things like that. Okay. So, that is what you are going to look at next week.